Essa apresentação é uma iniciativa da Faculdade de Engenharia da Universidade Estadual de Campinas. Meu nome é Paulo Curca e eu vou fazer a apresentação, então, do seminário e do nosso palestrante, professor Stefano Bruni. Esse seminário, ele também tem a participação acadêmica do Instituto Federal de Hortolândia, da Politécnica da USP, Universidade Federal do Espírito Santo, Unisanta, em Santos, UF Juiz de Fora e o Instituto Militar de Engenharia. E também nós queremos agradecer aos nossos parceiros que são coparticipantes desse trabalho, a Vale do Rio Doce, MRS, a Vale, MRS, Rumo, Green Beer Maxion, Amstead Rail, Abifer, Cimefre, RF, a Revista Ferroviária e a Associação Nacional dos Transportadores Ferroviários. Quem vai estar fazendo, então, a apresentação, esse seminário sobre dinâmica ferroviária, é o professor Stefano Bruni. Ele é professor titular do Departamento de Engenharia Mecânica do Politécnico de Milão, onde ele lidera o grupo de pesquisas em dinâmica ferroviária. As suas pesquisas lidam com dinâmica, vibração, estabilidade e controle ativo de sistemas mecânicos, com aplicações em dinâmica de veículos ferroviários, interação veículo-via, controle ativo e monitoramento de condições operacionais em veículos ferroviários, interação pantógrafo-catenária e vibração induzida pelo vento em estruturas de grande porte. Ele é autor de cerca de 270 artigos científicos e dedica parte expressiva de seu tempo às suas aulas e consultorias para empresas na Itália e em outros países. Ele liderou e continua liderando diversos projetos de pesquisa financiados pela indústria e pela comunidade europeia. É vice-presidente da IAVSD, International Society for Vehicle System Dynamics. Ele é editor associado dos periódicos Proceedings of the Institution of Mechanical Engineers, Part F, Journal of Rail and Rapid Transit, e também do Journal of Urban Rail Transit. Ele é membro do corpo editorial do Journal of Modern Transportation e do International Journal of Railway Technology. O professor Bruni é também membro do Conselho de Centro de Pesquisa em Sistemas Ferroviários, localizado na TU Graz, e é ex-membro do Comitê Científico do Instituto Francês de Pesquisa Tecnológica, IRT Rail Lineum. Eu passo a palavra agora para o professor Barufaldi, que vai dar algumas informações sobre a dinâmica desse seminário, então.
Okay. Obrigado, professor Curca. Então, bom dia a todos que estão nos assistindo, né? Meu nome é Leonardo Barufaldi, eu sou professor do Instituto Federal de São Paulo, e eu ficarei aqui na área técnica do webinário, comandando as coisas, né? Então, antes de prosseguirmos, eu gostaria de dar alguns avisos. Logo em seguida, o professor Curca repetirá essa apresentação que ele fez do professor Bruni, só que em inglês, e depois o próprio Bruni fará uma apresentação de cerca de 60 minutos. Terminada a apresentação, nós teremos, então, uma sessão de perguntas e respostas com cerca de 30 minutos. Essa sessão final, ela funcionará da seguinte maneira: a audiência pode mandar perguntas usando um formulário, cujo link está disponível na janela de chat. Eu vou repetir algumas vezes esse link durante a apresentação, para que todos possam vê-lo, e também ele está na descrição do evento no YouTube. Nós vamos organizar essas questões que chegarem pelos formulários durante a palestra, e depois nós faremos elas ao professor Bruni. Como o nosso tempo no final é limitado, talvez não seja possível responder todas, mas a gente vai procurar selecionar as que forem mais relevantes. Durante todo o evento, o chat do YouTube vai ficar aberto para comentários, mas nós optamos por usar esse formato de formulário separado para as perguntas, para deixar um pouco mais organizado. Então, é isso que eu gostaria de falar. Obrigado, eu volto a palavra ao professor Curca.
Good morning all, and welcome to the seminar on railway engineering. This seminar my name is Paulo Curca. I am from the University of Campinas, the Mechanical Engineering faculty. And we have a group of a research group on railway engineering. And we also are doing this seminar in cooperation with other academic institutions like the Federal Institute, the Polytechnic Institute of USP in São Paulo, the Espírito Santo Federal University, Unisanta in Santos, Juiz de Fora University, and the Military Engineering Institute. We also have some partners, commercial partners, namely Vale, MRS, Rumo, Green Beer Maxion, Amsed Rail, Ambifair, Cimefre, Railway Magazine, and ANTF. So we thank for those partners, and I'm going to present to you Professor Stefano Bruni, who is going to be presenting us his seminar. Stefano Bruni is a full professor at Politecnico di Milano, on the Department of Mechanical Engineering, where he leads the Railway Dynamics Research Group. His research interests are concerned with the dynamics, vibration, stability, and active control of mechanical systems, with applications to rail vehicle dynamics and train-track interactions, active control and condition monitoring in rail vehicles, pantograph catenary interaction, wind-induced vibration of large civil structures. He authored approximately 270 scientific papers and spent a large amount of time lecturing and consulting to the industry in Italy and other countries. He is, or has been, has been lead scientist for several research projects funded by industry and the European community. He's the first vice president of the IAVSD, the International Association for Vehicle System Dynamics. He's an associate editor of the Proceedings of the Institution of Mechanical Engineers, Part F, the Journal of Rail and Rapid Transit. He's an associate editor of the Journal of Urban Rail Transit, and he's a member of the editorial board of the Journal of Modern Transportation and a member of the editorial board of the International Journal of Railway Technology. Professor Bruni is a member of the advisory board of the Research Center Railway System, RCRS, established at TU Graz, and a former member of the scientific committee of the French Technological Research Institute, IRT, Rail Linium. So we thank you very much, Professor Bruni, for your disposition to come and present us this seminar, and I pass the word to you. Thank you.
Obrigado, Professor Curca. Thank you very much, Professor Curca, for your kind introduction. I will now go to my presentation. I hope you see my screen, unless I hear from you differently. So I can start. Let me first of all answer the question, what is vehicle dynamics? Because we are talking about vehicle dynamics. So vehicle dynamics is concerned with how a railway vehicle or an entire train set moves over a track, depending on the basic features of the vehicle itself, depending on the features of the track, and depending on other inputs and disturbances like the action of track irregularity, wind, and other factors. More specifically, for a railway vehicle, dynamics involves, first of all, a description of wheel rail contact forces, because, of course, the forces exchanged by the vehicle with the track play a fundamental, a key role with determining its movement. And then, in terms of practical implications of vehicle dynamics, we may include stability analysis for vehicles, analysis of curving conditions, longitudinal dynamics, evaluation of running safety, evaluation of ride comfort, and train-track interaction, which means the coupled vibration of the vehicle together with the track, with implications on vibration and noise. Rail vehicle dynamics also relates to other important problems in railway engineering, like damage in vehicle and track components, design for fitness and durability and maintenance of both vehicle components and track components, condition monitoring for the rolling stock and for the infrastructure, and also with railway vehicle aerodynamics. And I would conclude with saying that vehicle dynamics is an important branch of multi-body system dynamics, so that the general theory that studies the movement of complex mechanical systems. This is an overview of my presentation. I will try to address 4 main points. There is an initial part of the presentation which is a little bit more theoretical and clarifies the fundamentals of wheel rail contact, as long as it is useful to introduce vehicle dynamics problems. This is the little bit more theoretical part of the presentation. Then we will go into stability and curving behavior for a railway vehicle, which are 2 fundamental problems in the design of a railway vehicle. We will then talk shortly about ride quality, and finally condition monitoring. So let me start with a summary of wheel rail contact forces. In railway vehicles, we have steel-on-steel contact of the wheel over the rail, with large forces being transmitted over a very small contact patch. On top of that, we have a complex geometry of the wheel and rail surfaces. We have a nonlinear relationship of the forces to the running condition of the vehicle, and we have forces being generated by a combination of elastic deformation, local elastic deformation, close to the contact region in the 2 contacting bodies, and the effect of friction. So it is a very complex problem, and it requires rather complex solutions. Of course, I will not go through all of the solutions and methods and models, because it would be definitely too time-consuming. I will just clarify some fundamental issues. Let's say that the problem of defining wheel rail contact forces can be split into 3 steps. The first one goes under the name of geometric problem or contact point search. It consists of finding the position of the contact points between the rails and the wheels, given the relative position of the 2 bodies. Then the normal problem consists of finding the normal force exchange between the 2 bodies, given a normal approach between the 2 bodies. And finally, the tangential problem consists in computing the tangential forces, components of the contact force. That means the frictional forces developed between the wheel and the rail, once the normal load is known, and based on again on the relative motion of the wheel and the rail. In terms of contact point search, well, this can be addressed in different ways. I'm not so much interested with describing the details of how this can be solved, but let me just say that in the end, what you get is something like is summarized by the plots you see in this slide. So in the upper part here, if you can see my mouse, maybe I can use a pointer to improve. I see it. Maybe it was not such a good idea. Or I can put it to red and I can use this choice, okay? So in this upper part of the plot, you see the transversal profiles of the 2 wheels and of the rails, and you see the red lines connecting points on the 2 surfaces, which mean they show where the 2 profiles will become in contact depending on the relative position of the wheels over the rails. And when, like, the left wheel is completely displaced to the left, this means that the gauge corner of the rail makes contact to the wheel flange, like in this region, and on the other wheel-rail couple, you have a contact on the top of the rail with the thread of the wheel, and when you move back the wheel from left to right, then you have different contact positions, and contact points will move into an opposite position where the flange of the right wheel will make contact with the inner corner of the right rail. Out of this analysis, you can also find some important other geometrical parameters, like the so-called rolling radius difference. So that's the difference between the local rolling radius for the left and right wheel, which is caused by the conicity and by the, let's say, by the peculiar shape of the wheel profile. You can also find the value for the contact angles, the angle defining the slope of the tangent to the contact, of the common tangent to the profiles in the contact point. If we go back to the rolling radius difference, that's the difference of the two rolling radii in the central region of this diagram. So for as long as relative movements of the wheel over the rail are not too large, then you see that this can be approximated to a linear trend, which consists eventually in the definition of the equivalent conicity for the wheel-rail couple, which I will denote by lambda. Once this information is known, then we can look into the normal problem. So in the normal problem, we have the two bodies. Let's say this upper body is the wheel and this lower body is the rail. And we assume the two bodies are approached by some amount of delta, one to the other. And if they were not solid bodies, but rather just immaterial surfaces, then this would cause a compenetration that is shown by the orange arrows in this plot. But actually, because of the elasticity of the bodies, the two bodies will undergo some local elastic deflection, which will turn into local elastic deformation, eventually causing the formation of a contact patch having a finite size, which is shown here like the red ellipse. Now, there are different ways, again, to solve this problem. The simplest one being the very well-known and popular Hertz theory. In that case, we take one simplifying assumption. We consider a constant curvature for the two contacting bodies, for the wheel and for the rail, in the region of where contact takes place. And out of this and some other simplifying assumptions, like assuming that the wheel and the rail behave elastically like elastic half spaces, then we get the classic solution by Hertz, which states that the contact region is an ellipse, which is defined by the semi-axis A along the rolling direction and B in the direction perpendicular to the rolling direction for the wheel, and into an ellipsoidal pressure distribution where the maximum pressure is defined by this expression, which is function of the normal load N and of the sides of the ellipse, basically the product of the two semi-axes. But the Hertzian theory is not always completely accurate, and sometimes you need to resort to more complex models looking into non-Hertzian contact conditions, which means something like what you see in this slide, where you see that the shape of the contact is highly non-elliptic and the distribution of pressure is very far from the ellipsoid we used to have in the previous slide. Of course, in this case, the models you have to put in place are more complex. They are more also computationally intensive, which means if you are using these models in the context of numerical simulation in time domain, then you are going to, this simulation is going to be more time consuming because of the time required to solve the complex equations for wheel-rail contact, but it provides a more accurate description of wheel-rail contact, which is important both to define effects like curving and stability, which depend on the size and shape of the contact patch, but also have an effect on possible damage caused by rolling contact fatigue and wear, because this is highly affected by parameters like the maximum pressure in the contact region. Finally, we have the tangential problem. So here we assume, or we consider that we have a difference in the velocity of the two contacting bodies in the contact region, as long as we think of the bodies as rigid bodies. That is the orange arrow we have in this diagram. And this is compensated, this is counteracted, let's say, by, again, local deformation of the two contacting bodies, this time in tangential direction. So not in normal direction, which would be vertical in this sketch, but rather in tangential direction, which is the horizontal direction in this sketch. Again, this is pretty complex, and the solutions are very complex to describe. I will not dare to do so, but I will basically show you some results, starting from the simplest case, where we just consider a two-dimensional case with the wheel rolling over a perfectly rigid rail. We consider a Hertzian contact between the two, so we have an elliptic shape for the contact patch, which you see in this diagram below. We have no lateral or yaw movement for the wheel with respect to the rail, and we have a fixed rail as I said before. Then we define a longitudinal creepage parameter. This is a non-dimensional parameter defined as the ratio of the difference in the rigid velocity of the upper and lower body divided by a reference speed, which is in this case the average of the forward speed for the wheel center and of the peripheral velocity of the wheel while rolling with the angular speed omega. And we define the longitudinal frictional force Fx divided by the adhesion limit mu times n, where mu is the dry friction coefficient between the two bodies, to be a function, a nonlinear function of creepage. And we see, like when we start at very low value of creepage, then we have a very low force corresponding. The blue points you still see as points in this picture down show the direction of tangential stresses, tractions that are arising between the two bodies because of the effect of creepage. And when we increase creepage, so we differentiate more the speed of the wheel center with respect to the rolling speed of the wheel, then we increase these tractions. And you see that the contact patch gets divided into a region in blue color. That is where we have adhesion between the wheel and the rail, so we have no slip between the two bodies. And another part of the contact where we actually have slip between the two bodies. And when we further increase creepage, then you see that the point here moves up. So it means that while increasing creepage, we also increase the total force, and also we increase the size of the portion of the contact patch where we get slip between the wheel and the rail. And this is further increasing until we get into a saturation condition where the longitudinal force cannot grow anymore because it has reached the saturation condition. And in this condition, the contact patch is fully in slip condition, like this. Unfortunately, the situation with wheel contact is more complex because we have actually not only longitudinal relative movements in the contact point between the wheel and the rail, but we also have lateral relative movements. So we have a difference in longitudinal speed, delta Vx, a difference in lateral speed, delta Vy, and a difference in angular speed in normal direction, delta omega z. So we may define a longitudinal component and a lateral component for creepages and the spin creepage component. And we can define, let's say that the kinematic quantities defining these creepage components are shown in green here. And we can define three components of contact force and moments: a longitudinal force component Fx, a lateral component Fy, and a spin moment Mz, which are exchanged between the wheel and the rail, and they become a function of the three creepage components and of the normal force. And here you see just some qualitative examples of what we have when we just have a longitudinal creepage. Then we just have the longitudinal creep force, lateral creepage. In the contact we develop a lateral creep force and a spin moment, but zero longitudinal force. If we apply lateral creepage and spin creepage, then we get a lateral force and a spin moment. In case the contact patch is symmetric, like in this elliptic case, then we don't get any longitudinal force. This is again very complex to describe, and we need to simplify it in a way or another. So a very popular way of simplifying this is to take the assumption of small creepages, which means we just confine our attention to a range of contact conditions where the various components of creepage I mentioned before are all small. Then we can take a linear approximation for the relationship between the creep forces and the creepages, and this results in the very well-known Kalker's linear theory, which states a proportionality between the longitudinal creep force Fx and the longitudinal creepage νx through coefficient F11, and a proportionality between a linear relationship between the lateral force, creep force Fy, and the lateral creepage νy, and the spin creepage omega z through two coefficients F22 and F23. These three coefficients F11, F22, F23 being defined as function of the sides of the contact ellipse, so the product of the semi-axis AB, the G, capital G, tangential modulus of elasticity for the material of the wheel and the rail, which is assumed to be the same, and some non-dimensional coefficients, capital C11, capital C22, capital C23, which are defined as elliptic integrals based on the shape of the ellipse, so basically depending on the ratio on the A over B ellipticity ratio for the contact ellipse. This is only valid for an elliptic Hertzian contact patch, but it's very useful because it's a simple representation of the forces. Okay, now let us look at how this translates into an analysis for stability and curving. First of all, stability. What do I mean by stability? Well, the picture you see on the right is a photo that was taken in France. I think it was in the middle of the 1950s when a world record was performed on a French track, and the world record was fully successful. But when people went back into the track after the record train had passed, they could see that the track was completely misaligned. And it was realized that this was caused by a violent movement of the wheelset in lateral direction, which was later on recognized to be accompanied by a rotation. This is a sort of top view for the wheelset. So this is a rotation around the vertical axis, what is known as the yaw rotation for the wheelset. So a combined lateral and yaw motion of the wheelsets in the train, which was caused by a particular instability condition, which was then known as hunting. And it took a long time before this phenomenon could be fully clarified until, I would say, the end of the 1960s, before this was fully clarified. And then after that time, we are taking very seriously the need to perform a very accurate stability analysis as part of the design and also operation and maintenance of railway vehicles, especially for high speed. I will try to introduce the principle of stability using a very simple 2 degrees of freedom model, where I just consider one wheelset, which is attached to a bogie frame, which is just moving forward. This is again a top view with the two rails in the track shown by these thin lines and the wheel set in the top view, the primary suspension here with springs and dampers in longitudinal and lateral direction, the lateral coordinate y describing the lateral movement of the wheel set, and the other coordinate psi, angle psi, describing the yaw rotation of the wheel set. And the classic equations resulting from this model are reported here, where contact forces are described according to Kalker's linear theory I introduced before. So you see the F11 and F22 coefficients from that theory. And you see that we have two coupling effects. So when we consider the first equation, which is describing the lateral movement of the wheel set, we have a coupling term which is caused by the yaw rotation of the wheel set. This is because when the wheel set undergoes a small yaw rotation psi, then there is a small component of the forward speed in the vehicle which gets into the lateral direction, becomes perpendicular to the wheel's midplane. This calls for a lateral creepage nu y, which will in place call for a lateral, that should be Fy, actually not Fx, I apologize for this. Some lateral creepage force proportional to the creepage, which will, let's say, affect the lateral movement of the wheel set. And at the same time, if you look into the second equation, the equation describing the yaw rotation for the wheel set, then you see that we have a coupling term depending on y, which is caused by the fact that when the wheel set will move laterally, then due to the conicity of the wheels, one wheel will lose radius and the other wheel will gain radius. So you see that this term is also affected by the conicity of wheel rail contact we introduced before. And if we didn't have these two coupling terms, then the motion in lateral and the yaw direction would be completely uncoupled. But due to these terms, the motion becomes a complex combination of lateral displacement and yaw rotation. And if you are familiar with automation and control theory, then you may like this way of describing the problem in terms of block diagram, where this block describes the lateral dynamics of the wheel set, the yaw rotation of the wheel set. We get the angle of the yaw angle psi in output. This is multiplied by coefficient 2F22, like here, and provides the forcing effect to the lateral vibration of the wheel set, which provides as input the lateral movement of the wheel set, which is fed back through a proportionality coefficient, a gain coefficient, which is this one, and becomes the forcing effect for the yaw rotation of the wheel set. So this scheme shows that basically the phenomenon is a sort of a natural feedback loop that is developed for the wheel set. And if you have some familiarity with automation and control engineering, then you certainly know that when you have a feedback loop and you use too high gains for the feedback loop, and especially if you have a non-favorable phase for the feedback loop, then this feedback loop may become unstable. And this is actually what is happening in our case. If you like to see it in a different way, when you have the wheel set which is oscillating according to a sort of harmonic oscillation, then you get that when the wheel set is moving, let's say, to the left, which is up in this top view, then you have this combines with a yaw rotation, which produces lateral forces, which are also pulling the wheel set to the left, so that the instantaneous power of the contact forces multiplied by the velocity of the wheel set is positive. And when the wheel set goes back to the center position, so moves to the right, then also the inclination, the yaw rotation of the wheel set changes, becomes opposite, so that again you have the same direction for the lateral creep forces caused by the yaw rotation of the wheel set, and the movement of the wheelset. And in the end, this continues through the entire cycle so that you have continuously a positive power which is feeding energy in the vibration of the wheelset, so that the vibration of the wheelset, instead of becoming a damped oscillation, it becomes an expansive oscillation, which is just confined when the flanges of the wheel, of the two wheels, get in touch with the inner gauge of the rails. And because this contact can be very, very strong and very hard, very violent, let's say, then you may even get into the point that you can get a derailment for the wheelset, or you can get a permanent displacement in lateral direction of the track, of the rails. Let us now come to the curving behavior. And I will again resort to very simplifying assumptions, because otherwise the theory would be too much complex. I will assume the bogie, that we have two wheelsets connected in a bogie, and this bogie has very stiff suspensions. So there is no chance for the two wheelsets to have a relative yaw rotation, one with respect to the other. And because of the wheelbase of the bogie, then we have that the local radial direction at the leading wheelset, which is shown by the solid line here, is different from the local radial direction at the trailing wheelset, which is shown by the other solid line here. And this difference is defined by angle alpha, which is basically the ratio of the semi-wheelbase, so 1/2 of the distance in longitudinal direction between the two wheelsets in the bogie, and the radius of the curve. And due to this, if we look at how the velocities of the velocity vectors for the centers of the different wheels are pointing, as this is the center of curvature for the trajectory of the entire bogie, then we see that there are angles formed by these velocity vectors, which are causing a so-called attack angle between the wheelset and the track. And this causes some, again, transversal creepages. So there is a component of these velocity vectors which goes into the transversal direction for the wheels in the direction perpendicular to the wheel midplanes, again calling for creep forces that are arising. So if we consider a very simple situation where we have the bogie with infinitely stiff suspensions, and also we assume we have relatively small creepages, so we may use the theory by Kalkar we have seen before. We assume there is no flange contact between the wheels and the rails, which is a very, let's say, a highly simplifying assumption in this case, but otherwise, again, we would get into a too complex case that could be only possible to solve by numerical means. If we stick to these simplifying assumptions, then we find that we have, even if we consider the bogie running at compensation speed, which means centrifugal effects due to the curvature of the track are fully compensated by the cant we're applying in the track, then we have that we have transversal creep forces arising on the leading axle and on the trailing axle. And because you see these opposite forces are generating a moment which tries to yaw the bogie in a clockwise direction, then this must be reacted by longitudinal creep forces arising at the four wheels. And I would like to stress on the fact that all of these forces that are represented by the blue arrows in this plot, they are all, let's say, not needed for the vehicle to, or for the bogie to get into a balance of centrifugal forces, because this is already guaranteed by the cant of the curve, by the compensation. So these are unnecessary forces that are still arising because of the specific way the bogie is running through the curve. And even when we make the picture more complex by introducing a saturation of wheel rail contact forces, by introducing flange contact between some wheels and the corresponding rails, then it still remains that there is an excess of frictional force being generated while the vehicle negotiates a curve than the minimum value of frictional forces, of creep forces that would be needed for that. And of course, all of these frictional forces are causing damage and wear, both in the rails and in the wheels, which is highly unwanted. So the question ultimately is how to design the vehicle to have good curving performance, which means especially avoid developing excessive wear, excessive damage on the rolling surfaces as a consequence of curving, how to make sure that the forces are not large enough to be harmful to the safe running of the vehicle, and at the same time, how to guarantee a good stability for the vehicle. Unfortunately, these two goals turn out to be in conflict one to the other. If you want a design for good curving, then you want a flexible suspensions that, contrary to what I was showing in the previous two slides, will allow the wheel set to align radially, compensating for the effect I was showing before, and allowing to reduce wear and damage in the wheel set, reducing creep forces, improving safety, and so on. But soft suspensions will be, let's say, harmful, can be shown to be harmful to stability. To get good curving behavior, we'll also want to have a relatively high conicity so that the conicity of the wheels can compensate for the different length of the outer rail compared to the inner rail. But this is again harmful to stability and so on. So how can we solve this design conflict? Well, apart from a passive optimization of the vehicle, which is the classical way which has been followed since the start of the modern design of railway vehicles until a few years ago, now it is more and more frequent the use of active suspensions. So the first example I would like to show is active primary suspension with an example from Bombardier, which is published. And here you have longitudinal actuators. You see the red arm here, which is moving back and forth the axle box based on an actuator, which is basically formed by this green lever. So this is capable of creating a desired yaw angle for the wheel set, or apply a yaw torque on the wheel set, which will control the movement of the wheel set, inhibiting instability. If we go back to the feedback control loop that we considered before, which is here shown by the part of the picture with a blue shade, then we can add another feedback loop, which is created by active control, which can be designed to, let's say, cancel the effect of this instabilizing effect. Of course, having an actuation system at the primary suspension level can be challenging in terms of making sure that this can be designed to be safe enough, reliable enough, and so on. So in other cases, you may want to apply some active control between the car body and the bogie, so at a secondary level. And this is an example of an electromechanical actuator used to apply controlled torque to the bogie between, let's say, the car body and the bogie. And this goes back to a research we were performing with Alstom some years ago. More recently, people have started to think about semi-active solutions, and I'd just like to show you a concept for a semi-active yaw damper. We have been developing quite recently with CRRC, the Chinese company, let's say, railway vehicle manufacturer, and so far this concept has been tested in our labs according to a harder-in-the-loop test. But I don't have time to go into details of this. If you have questions, I would be happy to answer your questions. And finally, you can use active steering, which is normally more frequently used for low speed vehicles for low speed with which have to travel very narrow curves, so for urban environment like trams and metro vehicles. Let me now go into ride comfort, ride quality, which has to do with passenger comfort. And the rationale behind this analysis is that when the vehicle is sitting in the car body of a vehicle, then it is subjected to vibrations, and these vibrations will cause a discomfort sensation for the passenger, which is related not just to the intensity of the vibration, but also to the frequency at which the vibration happens. And here you have a logarithmic diagram for frequency showing the frequency ranges where different parts of our body, like the stomach, the chest, the eye, and so on, are affected by vibration. This typically results in weighting curves which weight the importance of vibration in different frequency ranges. And this is the example defined by European standard EN 12299. So in the end, we have track irregularities exciting the vibration of the vehicle. We have the dynamics of the vehicle, which is excited by track irregularity, like in this very simple model with just 1 degree of freedom, the vertical motion of the car body X as a function of the excitation from track irregularity. If you use this very simple model, then you get into this transmissibility diagram, which is the ratio of the motion of the car body over the amplitude of the irregularity plotted versus frequency. And of course, you want this transmissibility ratio to be as small as possible and clearly lower than 1, so that you can filter out the effect of irregularities and ensure a better ride quality for the passengers. So the lowest this line, the better the situation. And you see that this you get when you have damping C in the suspension, which is reduced to 0. In that case, you can reduce the vibration, let's say, to 1/3, 1/5 of the amplitude of the irregularity. But unfortunately, then you get a higher vibration when you get into the resonance condition and when you get into slow, low frequency effects, like the effect of gradients in the track and things like that. So you cannot reduce too much damping. And then again, you are faced with a conflict between using a too low damping or a too high damping. On top of that, you have another problem which is related to car body flexibility. Modern car bodies are very flexible, and then some of their resonances related mostly with the bending, but also with torsional modes of vibration, are falling in the frequency range which is relevant to passengers' comfort, to ride quality. So what you see here is an example of a measurement, of a line measurement we performed with a vehicle equipped with different accelerometers installed on the floor of the car body at different locations. You see labeled as A, B, C, D, and so on. And you have a comparison here of the vibration measured at point B over one bogie and at point E in the center of the car body. The lower diagram is for the time history, where you see you have a larger vibration at point E compared to point B. And the upper diagram is the spectrum of the signal, where you see that most of the vibration at point B is concerned with the frequency range of between 1 and 2 Hertz, which is related to the rigid motion of the car body over the suspensions. But at point E, you have a very significant contribution in the frequency range between 6 and 7 Hertz, let's say, which is related to the bending vibration of the car body. So you also have to control this effect. So how to control at the same time rigid body motion and flexibility effects? You have 3 options. The classical option is to use passive suspension. So in this simple scheme, you have the primary suspension here. A label is missing, I apologize for this. Secondary suspension between the bogie and the car body. And you may opt for active or semi-active suspensions at the secondary suspension level, so replacing the passive damper by an actuator or a semi-active damper here, or you can use active or semi-active primary suspensions. So you're replacing primary passive dampers by either full active actuators or adjustable dampers. This is an example. I don't have time to go into the fine details of the different approaches you may have with this, but I will be happy to answer questions on this. I just want to show you an example which is coming again from a project we are following with in cooperation with CRRC, where we have tested both semi-active primary and semi-active secondary suspensions. So in the case of semi-active primary, you have a very limited benefit in the frequency range between 1 and 3 Hertz, which is related to the rigid motion, but you still have a good effect in the frequency range around the 8 Hertz, which is related with the first bending mode of the car body. If you resort to semi-active secondary, then you can have a good improvement here. Sorry, I missed to mention that the red line is for the passive vehicle and the blue and green lines are for different scalings of the semi-active suspension. So you can improve both the response of the car body in the frequency range related to rigid body modes and to the first bending mode. I'm afraid I will need to skip my slides about active pneumatic control. So I have maybe 5 minutes to talk about condition monitoring. While condition monitoring maybe is not directly related to, or is not really one part of vehicle dynamics, but it has a very strict connection. And I can say there is a very strong motivation for considering condition monitoring of railway vehicles nowadays. If you talk to an operator in Europe and even to an infrastructure manager in Europe, they will always tell you, we want to reduce maintenance costs. And the way we would like to do that is to improve our condition monitoring so that we can know better the condition of the rolling stock in the case of the operator and of the track in the case of the infrastructure manager, and then we can optimize our maintenance strategies based on this knowledge. Of course, it's a very ambitious and very complex task, but something can be done and rapid progress is being made. And I would like to show you just some examples. One example we are following in cooperation with Lucchini. Lucchini is a very important company in Italy manufacturing wheel sets, especially, but not limited to high-speed vehicles. For instance, to my knowledge, they are supplying all of the wheel sets for Chinese high speed, which is the largest market for high speed in the world. They are now considering, and we are supporting them in this, to have instrumented wheel sets which allow a monitoring of in-service stresses together with monitoring of in-service vibration. This can be used for different purposes: to know about the condition of wheels, to recognize the effect of wheel flats, to know about stresses and then improve the design and also adapt for the periodicity of non-destructive testing of axles to find the presence of fatigue cracks in axles. We are also considering the chance to use these instrumented wheel sets to provide a continuous in-service health monitoring of railway axles. In Italy, we were really shocked some years ago, it was 2009, by the tragic accident in Viareggio. So we are spending an effort, let's say, to make sure that this will never happen again. And one way is to have continuous in-service health monitoring of railway axles. So if a crack is propagating in the axle, then you can recognize the presence of the crack from the so-called breathing mechanism, which means while the axle is rotating, the crack will open and close due to the opposite effect of bending forces acting on the axle, and then this will turn into some distinctive features of the bending vibration of the axle that can be measured and recognized. And then, according to our laboratory tests for the time being, we were able to detect a crack size which was 4% of the total resisting area in the axle, which is still in the starting phase, so you can rule out this axle before it gets into a dangerous situation where the axle could fail and cause an accident like the one I mentioned about PH. Another important topic is with another type of instrumented wheelset. This is to measure wheel rail contact forces, which can be used for several purposes, including the homologation of new vehicles. This is a very expensive measuring setup, so that's not for equipping a very large number of wheelsets in service, but it's still for experimental vehicles. It's still possible, and it is done. And this is the system we developed for the ETR 1000 high-speed train, the new generation high-speed train in Italy. It was tested in the Italian high-speed line up to speeds slightly above 390 kilometers per hour. And here you see one example of the measurements with a very stable and well performing a signal from our system. Another important topic, I'm really approaching the end of my presentation, is about monitoring and prognostics of bearings and gearboxes in the traction unit of a railway vehicle, of a locomotive, or of a distributed power train set. And in this area, we did a lot of research. I would just like to give you an example with a test rig we established together with Bombardier, which includes a traction motor, a gearbox, bearings, and then a brake motor, which is used to feed back, to operate, to brake the drive unit, and then to feed back power into the traction motor. There we applied the initial defects which were generated artificially, and we could see how these defects were growing with time, and also which were the best acceleration and temperature signals suited to spot out these defects in their early stage, avoiding catastrophic failures in the drive unit. I will conclude with this example. This is totally different. It's a portable, let's say, condition monitoring unit. This is a €1 coin to give you an idea of the size of this unit. I'm aware that euros are not in use in Brazil, but this coin has a diameter of 23 millimeters. And the unit is nice because it includes an energy harvester unit, a system. I apologize for words in Italian here, but I hope you can still get the point. You have a small battery, a unit for managing a power, a microcontroller, then a 3-axle accelerometer, a temperature sensor, and then also a low consumption Wi-Fi unit that is able to transfer the measured data to a receiving unit on board the vehicle. So this is very nice for equipping for a sort of revamping of existing units with providing these existing units with a condition monitoring capability. I think this is my last slide, so I thank you for listening. I hope I was keeping the time more or less 15 minutes, and of course I will be very pleased to answer your questions.
All right, thank you, Professor Bruni. It was a very good presentation. Almost complete railway dynamics course, followed by some of the recent developments. And we have some questions here. Just let me refresh again the form here so I can check if anybody has asked something more. Okay, so here we go. I will try to organize the questions more or less on a chronological order here. So let's move on. So first one comes from Pedro. Pedro is a student at UNICAMP, and he's asking you, how can you use automation and specifically computer vision to help improve safety and performance in vehicle dynamics?
Okay, thank you, Pedro. This is a very interesting question. the first point that comes to my mind is vision can be used to improve the monitoring of the infrastructure. So going back to the last part of my presentation, you can, in this moment already, the monitoring of the track geometry, which is very important, and not only in view of ride quality for passengers, but also in view of the safe running of vehicles, is monitored by optical systems, which are often combined to accelerometric systems. So this is already existing, but of course, it may be improved. You may have situations like in bad weather conditions when you have snow, or when you have other types of bad weather conditions when cameras will work on not at the top of their performance, and then you may have issues with this. Another important topic is with monitoring the quality of the overhead line when you have electric power fed by the overhead line through the pantograph into the vehicle. Then you can recognize by artificial vision, you can recognize different types of defects happening in the catenary system, in the overhead equipment. So this is one area. Of course, there are also other areas like one other area is that more and more we have ATO automated driving units in place. So in many metro systems, we now have driverless cars, and then there is a safety issues with recognizing obstacles or issues in the track, and then visual systems can be very useful in that regard. That is the two main areas where I would see a very big help from artificial vision. I hope I answered the question.
Well, thank you. That's great. Pedro will answer us if it's okay, then later. Let me see here. We have some questions. I have one here about tribology. I think it's a link between simulation tests, which I think is very interesting. It comes from Lucas Biazon, which is with the Technological University of Paraná, here in Brazil. Okay, so he says the following: one difficulty from tribologists when studying lubricant performance, like greases, on the wheel rail interfaces is to estimate the contact kinematics. He's talking about specifically the magnitude of the creepages, right? And he asks the following: from your knowledge, is it possible to estimate the common range value of slippage between wheel flange and wheel gauge corner for tight curves to be used as input for tribological testing? For instance, a twin disc or something like that?
Well, it's a bit harder. So first of all, yes, let's say the use of lubricants is very, very important in many cases. So because of the limited time, I did not have time to cover all the topics. But of course, you can improve curving by the use of by the proper use of lubricants. Let's say in the flange, you normally expect to have larger values of creepages compared to the tread of the wheel because of the larger rolling radius difference that applies to the wheel flange. But of course, you may have different situations depending on the friction coefficient. So normally, you may expect a larger creepage where you have a lower friction coefficient, because then you may get into a situation where you have a double contact point, one contact point arising between the top of rail and the wheel tread, and the second contact point arising on the same wheel rail couple between the wheel flange and the inner corner of the rail. And then whether you get more creepage, more slip, let's say, on one or the other of the two contacts, it depends, of course, on where you have more friction. The larger the friction, the lower the slip you can expect, because friction will make the two bodies stick together, let's say. And at that point, and then because of the difference in the two rolling radii at the two contact points, then in the other position, you may expect a rather large amount of slip, or at least creepage. Then, let's say, to simplify my answer, I would say, if you have contact on the flange and you don't have a very large friction coefficient between the rail and the wheel flange, then you may expect relatively large creepages. Let's say probably about around 1% or more in the flange area.
Great, thank you. I hope this answers the question that comes from Lucas. Now, moving on to a more, we have some questions here concerning condition monitoring, to be true, that were made by Professor Guilherme from the Federal University of Espírito Santo and Professor Oteliano, and they are more or less related. So I will start with the question from Professor Guilherme. So he says the following: in Europe, when a railway company wishes to buy new vehicles, they should be evaluated and improved according to some of the EN standards, right? Especially concerning overturning or this type of catastrophic event. So he would like to ask you if you can just say some of the main tests that are mandatory to approve a vehicle in Europe, including an idea of costs of those tests. And he asks also if you have to do field tests or just simulations are enough to approve a new vehicle.
Yes, okay, yes. Okay, the European standard, let's say, well, of course, there are a range of standards addressing this problem. Let's say, I will not include in my answer all of the standards that are related to proving that all components in the vehicle are fit to purpose, like the railway bogie, the bogie frame, like the wheel sets and so on. So when we talk about, let's say, having already proved that all bodies can withstand the in-service stresses without leading to failure due to fatigue or other damage mechanism, then you still have to prove that the vehicle is properly running over the track in a way that will avoid any derailment or any other safety issues. And then the relevant standard in Europe is EN 14363. And this is a quite complex standard. It involves some initial tests which are relating with initial proof that the vehicle is working properly. And these are normally done on static test stands. And when these tests are satisfied, let's say, then the vehicle gets a temporary approval for being tested in the line. And then there is an extensive session of tests in the line. The instrumented wheel set I showed, you probably see it again, was actually part of the homologation test for the ETR 1000 train, because then you have to measure wheel rail contact forces in vertical and lateral direction, and you have to prove that these forces remain within allowable ranges. You have a number of indicators of safety, related indicators that have to be to stay within suitable ranges. And this is a really extensive and time-consuming and effort-consuming process. To give you an idea, the homologation for this train, of course, was a very sophisticated train, the brand new top-speed train in Italy. So it was a complex process because of the ambitious project. But the homologation phase, the line test for homologation, took more than 1 year. And the effort involved is huge, as you may imagine. And also the economic value of the trains being held on steel until this long process is completed is very, very serious. This means that recently the European industry of manufacturers of railway vehicles have looked for ways to simplify this process, and as part of that, numerical simulation has come into play, but just with a limited scope. Like when you want to extend the homologation for an existing vehicle, then you can prove based on a comparison between a mathematical model, a multi-body model of the vehicle, and previous tests that the multi-body model is sufficiently accurate, and then you are allowed to use the multi-body model for some parts of the extension of the homologation. But if you need to start from scratch for the homologation of a brand new vehicle, then you still need to go in the line, and you have a very big effort related to that.
Okay, thank you. So it's a rather cumbersome procedure, right?
It is indeed a big issue with railway industry in Europe. Very big, very serious.
Yes, those tests, they apply for passenger vehicles as well as heavy haul vehicles, or just passengers?
For any vehicle, including locomotives, passenger vehicles, freight cars, yes.
Okay, great.
But it's just it's just a type test. So if you produce more vehicles with exactly the same design, you don't need to, to go back. So basically, because freight wagons are of old design, you just trust the previous homologation. You don't need to have the homologation, unless, of course, you go into a brand new design for the freight car.
Great. All right, thank you. Well, next one here, as I said, moving on to condition monitoring. Professor Oteliano asks here, he says, we here in Brazil, we are currently working on developing indirect measurements of contact forces using accelerometers in the car body. Okay. Do you know any initiatives that work well in this direction of using the accelerometers to get the contact forces in some way?
It is not an easy task, I think. Personally, I don't recall attempts and papers covering this area. I think it is a difficult task because you have two stages of suspensions which are isolating the vibration of the car body from the wheel sets. So I think you can basically identify wheel rate contact forces in a limited frequency range, which will probably not include the very low frequencies, because then accelerometers will not be probably sensitive enough to very low frequencies. I'm talking about fractions of hertz, where variations of wheel rate contact forces are related like to curving of the vehicle and things like that. And I think they would not work either in a high frequency range like above 10-20 hertz, because then you have too much effect of suspensions that filter out the effect of wheel rate contact forces towards the car body. But of course, that is just my opinion. Let's say based on I was not thinking about this before, so I'm certain you can find a proper way to manage this. But I'm not really aware of previous investigation in this area.
Okay, thank you. I have a question from my side related to this. Earlier this year, we have been talking at UNICAMP about measuring lateral and vertical forces using strain gauges attached to the rail instead of using the instrumented wheel set, because they are very expensive and most Brazilian companies just don't have the money or don't want to use the money to spend on such a expensive piece of instrumentation. Have you ever heard of anybody that's been successful in measuring lateral and vertical forces using the rail instead of the rolling?
Oh yes, this is completely possible. There are many. Well, I think you can also find papers on this, and it's I would say it's a quite well-established technology. Basically, it works in a similar way like putting strain gauges on the wheelset. Of course, it's a simpler setup because of the simpler geometry of the rails, and also because you don't need, well, the problem with the wheelset is that the wheelset is rotating, so you need some kind of telemetry to transfer the strain gauge signals from the rotating body, the wheelset, to the non-rotating part of the vehicle, so to the body frame or car body. And this can be done either by analog or digital telemetry, which are anyway very much expensive, a little bit delicate as an equipment, and so on. So this is why mostly putting strain gauges on wheelsets is expensive compared to putting strain gauges on rails. The drawback of using strain gauges on rails is that you just get a measure of the wheel rate contact forces while the single axle passes over the instrumented section of the rail. So if we are considering a European standard, the N14363, the one I mentioned before, then you need to measure wheel rate contact forces over very long portions of the track, because you need at least 25 sections, each one at least 500 meters long, if I recall correctly. So it's a longer measuring record, and clearly you cannot do that with strain gauges placed on the rails. But if the aim is just to measure wheel rate contact forces along a limited region of the track, then of course using strain gauges on the rail is a winning solution, is a much simpler, much more affordable solution.
Great, thank you. Next, we have a question here that was made by Professor Paulo Kurka from UNICAMP. And he's asking more about the modeling of the vehicle now. Have you ever come across a strategy of modeling the dynamics of the wheel set as that of a rigid rolling double cone? I think he's imagining the wheel set as a big cone with two points. And yes, have you ever?
Yes, this is the classical model, the so-called Bicone model, and it is, let's say, not far from the model I used in this slide. So although in the picture, this slide, although in the picture you see the wheels as having some kind of flange and so on, actually we are just considering a conical profile. So this is more or less, it is indeed the model for a bicone, which is just moving in lateral and yaw direction. Of course, this is, I would call it the classic basic model, and there are several complications that you can put on top of that, like you can consider the coupling of lateral motion with roll motion, which is created by the geometry of the bicone. You can consider the effect of spin creepage, which is neglected in this case, and you can consider other effects not included here. I tried to use the simplest possible equations just to clarify the principles of stability, but of course it's possible to make this model more complex. You can include gyroscopic effects, for instance, and so you can get a more detailed model. But of course, then you can also include a number of other effects. As long as you stay with the rigid bicone, you can probably solve the model by analytical means or by semi-analytical means. When you move into more complex descriptions, you include more than one wheelset, the bogie frame, the car body, the suspensions. Maybe you also include flexibility of different bodies. Then you go into a complex multi-body model that you can just solve numerically.
Okay. So we had an explosion of new questions in the last few minutes. I will try to filter them, right? I'm sorry, I will not be able to answer all of them, so I will select some here. Okay. Well, I think there are two here which are different, so let's go to them. So Professor Otteliano asked you if you are using or studying composite materials for buggies in Italy or in Europe in general.
Yes. Actually, originally, I had in mind to include a small portion of my talk about the lightweighting of railway vehicles. Then I realized that I could not make it in the time available for this talk. But yes, of course, now one of the keywords for research in Europe is to achieve a lighter weight for vehicles. And this, of course, includes the use of non-metallic materials, of composite materials. And I would say this is already brought into, something that can be used in real service as long as we consider small units like for interior parts or parts of the car body or maybe the bolster and so on. For the bogie frame, we have some examples. Different companies have considered bogie frames made out of carbon fiber materials. The problem here, I would say, to my knowledge, is there is not a railway-related standard in place for proving the fitness for purpose of a railway bogie frame made out of carbon fibers. So this is one problem, because you can build it, you can show it on a stand, you can also perform a fatigue test to prove that it's fully suitable, but then it is not included in the standards, and probably a railway, a national or European railway agency will not accept that this is put into service with passengers. I also would like to take the opportunity very quickly to show one slide about one project. This is very futuristic, let's say, visionary, not for tomorrow, for maybe 10 years from now. That's the idea of replacing the steel axle by a carbon axle, by an axle made out at least partly of carbon fiber material. And you see three concepts that were developed in a project which is called the Wheelset of the Future. This is funded by a funding program for research in Europe about railway engineering called the Shift to Rail. And you see that if you compare the weight of the initial or the benchmark steel axle, it is nearly 200 kilograms. But with the use of carbon fiber material, we were able to lower it down to approximately 80 kilograms, so more or less 40% of the original weight. Reducing the weight of the axle of the wheelset is particularly important because this is the so-called unsprung mass. This is the mass that comes directly in contact to the rails. So it is directly responsible for vibrations, for dynamic loads applied on the track. So for noise, for vibration, for damage on the rails, and so on. So it is more important to lose weight on the wheelset than on the bogie frame or on the car body. Of course, the savings you can make on the wheelsets are more limited than on the car body, but still they are very, very important. There are, of course, a number of problems related with this, with the safety and so on, but so far we could design a concept that provide the same resistance to loads and the same flexibility as the benchmark steel axle. And then we need still to consider a number of problems like the impact with stones in the ballast or other effects. Fire and toxicity is also an issue.
All right. Well, that's a really interesting development. You see, in automotive engineering, it's so usual to talk about reducing the unsprung mass, and in rail engineering, we haven't been worried about it until recently, right? It's not, so it's,
yes,
it's quite
this is
new.
right. That's mainly because safety prevails over every other point of analysis. So you will never want to compromise safety, even if this brings a big advantage in terms of like reducing unsprung masses. Sure. But things are slowly changing, I think, or Great. At least meaning that I do not mean that we can, let's say, relax our requirements on safety, but rather I mean things are changing because we are more and more able to prove that we can use new innovative light materials with guaranteeing the same level of safety as traditional steel materials.
Sure. Well, I think we will move on to our last question here. Unfortunately, our time frame here is going away. It's an interesting question. It comes from Arturo Cancellieri. He is a student at UNICAMP as well. And he has two questions. Both are related to the same thing. So I will ask them together, okay? The first question he has is, how do you see machine learning techniques being used for condition monitoring? And the second one is, if you know any examples of unsupervised learning being applied to help out maintenance decisions.
Yes, very good question again. Yes, I was even mentioning this in one slide, although I didn't have time to say this while I was talking about this slide. No, maybe I decided to remove this because of time limitation. But yes, in the case of condition monitoring, of course, machine learning techniques may play really an important role. So I think then the problem is you need to work out a very good initial selection of useful features that you are extracting from the measurements you take on the vehicle and or on the infrastructure, and then you can really use machine learning techniques in a very powerful way. I think it's a quite a new field, so I have started seeing approaches to this only during the last very few years, maybe the last 3 years or maximum 5 years. The number of publications on this is still quite scarce. I mean, strictly related to the railway area, but already there are some papers on this. There is one paper a PhD student of mine published together with some colleagues at KTH Stockholm while she was having a research stay there in Stockholm as part of her PhD. There is also an interesting PhD thesis from a researcher working at Siemens. Unfortunately, because this is industrial research, I think the thesis is subject to confidentiality, and I'm not sure how much this guy will be able to publish out of his work, but he was doing an excellent work. I was the opponent with the final discussion of his thesis. So just to say that there are a number of attempts, and many of these attempts show a really large added value from machine learning, while unsupervised learning techniques is a little bit a frontier now. So I think we need still to do some research before unsupervised learning can be used for this purpose, but certainly this is something that is going to become more and more important in the near future, in very few years from now. And I think it's a very, very interesting topic for research. So if the person who asked this question is working in this area, I think it's a very, very interesting area. It's going to be, I think he will be satisfied with doing research in this area.
Yeah, well, I can tell you Arturo is making research on this area.
Yeah, okay, then Arturo, it's a good choice, and go on with that, definitely.
Great. Well, Professor Bruni, thank you for your attention, for your presentation, for the quality of the answers you gave us. I think we will stay here with the questions, looking forward to the future for machine learning and big data. And I have to thank you on behalf of the organizing committee, and I will give the word to Professor Guilherme and to end the presentation. Okay, thank you.
Thank you very much, Leonardo.
Okay, thank you, Professor, for sharing this time with us. It was very interesting time. Thank you very much. Pessoal, obrigado por todos que estiveram aqui com a gente. Esse foi o nosso terceiro webinar internacional. A gente vai deixar o vídeo gravado no YouTube e avisá-los que a gente está planejando um quarto e último webinar dessa série do Simpósio Ferroviário para acontecer em fevereiro do próximo ano com o professor Untitled da Faculdade de Engenharia Civil da Universidade de Sydney, e o tópico será sobre engenharia civil. Então, eu queria agradecer a todos pela presença e que tenham um bom final de semana e até a próxima. Obrigado. Thank you.
Obrigado. Thank you very much, and have a good weekend to everyone. Goodbye. I hope you enjoyed.